solving this problem, you'll probably want to take a moment to pause the video and familiarize yourself with the question just a bit. If we know that we are using Newton's law of cooling to estimate the time of death, we know that we are going to want to start with our Newton's formula. So T equals C plus T sub 0 minus C e to the power of kT. Just a couple of reminders. T is going to be our measured temperature after a certain period of time. C is our temperature for the environment. T sub 0 is the initial temperature. K is our constant that is going to determine the rate at which the temperature is changing. And then, of course, lowercase t is our variable for time. We are going to be measuring time in this question by hours. That's going to be determined by this indicator right here, where after 1 hour we were making our second measurement of the temperature. We have two sort of competing temperatures here. The first one is, as soon as the detective arrived on the scene, they measured a temperature of 80 degrees. And then after an hour had gone by, the temperature was measured again at 78.5 degrees. Both of those temperatures cannot be used together. They both would occupy the spot of capital T in our formula. Instead, we're going to use the formula twice, once for 80 degrees and once for 78.5 degrees, and see if we can manipulate them algebraically in some way to bring them together. So we're going to have two different applications of the formula used here. First, we know the temperature dropped to 78.5 degrees. The room's temperature was a given 68. We assume the initial temperature of 98.6 degrees. And that was measured an hour after the detective arrived. So our variable in this space is just going to be the amount of time since death plus 1 hour, because 1 extra hour had gone by. Our other measurement of 80 degrees, this application is going to be very similar in its construction with one major difference. When we get to our exponential factor at the end, we're not going to have to worry about that 1 because this was the initial measurement. We're just going to say the number of hours since the person died. Doing a little bit of algebra and simplifying, we can subtract 68 from both sides. We can subtract the inside of the parentheses. This is going to be e to the kt plus 1 still. Over here, the same thing, 12 equals 30.6 again, e to the kt. A little bit of division and a little bit of simplifying. You can check this simplification, but if we divide this side by 30.6 and this side by 30.6, and we don't want to have to carry a lot of decimals inside of fractions, that division is going to simplify to 35 over 102, e to the kt plus 1. And then over here, a very similar kind of simplification, but this time it's going to end up as 20 over 51 is equal to e to the kt. The key to bringing these two equations together is to recognize that this power of the exponential part can be rewritten as kt plus k. Because it can be rewritten as kt plus k, this entire term can be split into e to the kt, e to the k. Because I know that e to the kt has to equal 20 over 51, that 20 over 51 can take that spot right there and allow us to join the two equations together. So now, putting all of those together, we have 35 over 102 equals, remove e to the kt from the left side and replace it with 20 over 51, but then leave this e to the k here as still part of our work. Dividing both sides by 20 over 51. And simplifying, we get that 7/8 is equal to e to the k. Using what we know about the natural log, we know that the natural log of 7/8 is equal to k, which gives us an approximate value for k of negative 0.134. Now that's rounded. There's a lot more decimal places after that, but this is going to be our approximate version. So looking at our work so far, we took the two pieces of information that we had, the two measurements, the first measurement at 80 degrees, the second measurement at 78.5 degrees. The 78.5 degree measurement happened after the 80 degree measurement, so its time needs to be a little bit longer. Simplifying normal algebra, recognizing that we can rewrite this power, allows us to join the two equations together, and then a little bit of careful algebra and arithmetic gets us to a value of k of negative 0.134. Obviously, that's not the time. That's not the time since the person had died. So we're going to use this k to help us figure out that time. And we're going to go back to this spot right here, because we now know what k is, and this is the simplest version of all of our work involving k and t together. This is the simplest spot right here for us to do a back substitution. So now with the back substitution, we're going to say 20 over 51 is equal to e to the negative 0.134 t. And again, using what we know about the natural log, we're going to say the natural log of 20 over 51 is equal to negative 0.134 t. And then we'll finish by dividing both sides by negative 0.134. And this evaluation right here is the one we're going to use to determine our time. A little bit of careful typing, making sure your signs are correct and your parentheses are all in the right spot. And we get an approximate time of 6 hours and 98, excuse me, not 6 hours and 98 minutes, 6.98 hours before the first measurement. Now, we understand going in the limitations of using technology to help us with this. As soon as we rounded this number, we knew we were not going to get a perfectly accurate estimate. We also made an assumption at the beginning that the body temperature was originally 98.6, which isn't necessarily guaranteed either. Some people are slightly above and some people are slightly below. But going in with this sort of basic assumption of somewhere around 7 hours, I can look back at my original question and see that the detective got there at 10:23 when she started her investigation. So if we go approximately 7 hours before 10:23, we can estimate a time of death at around 3:23 p.m.